Hello everyone. For our EECE 506 YouTube project, we are gonna introduce you the engineered yeast as a biomanufacturing platform on Mars. And our team member are August, Stephen, and Yuefeng. First, we want to discuss why we chose Mars as our colonization target. First, it is Mars is the closest habitable neighbor of Earth, and which makes travel there plausible under current human technologies. Space traveling is still a gigantic challenge, but it's not insurmountable. Mars is also close to Sun, so it receives decent amount of solar radiation. Its atmosphere consists mainly of carbon dioxide and nitrogen, essential for plant growth. And last but not least, Mars has almost the same self-revolution periods, 24.6 hours as Earth, and similar season cycles as well. But Mars is not as hospitable as we expect. The much lower gravity, approximately 38% of that on Earth, will impose severe health effects such as bone loss, atrophy, cardiovascular problems on humans. The low gravity also weakens Mars' ability to retain its atmosphere. Consequently, the atmosphere is so thin that the greenhouse gas effect on Mars nearly does not exist. So the temperature varies from 150 degrees Celsius below zero to positive 20 degrees on daytime during daytime. Moreover, the thin atmosphere cannot block UV radiation, which elevates the probability of skin cancer for humans on Mars. Despite all that, its atmosphere, composed of 90% of carbon dioxide and only 0.13% of oxygen, lacks the vital gas for human survival. And essential resources for humans, such as water, food, and fuels, are also scarce on Mars. One solution resides in the engineered microbes, or yeast, which can produce food, fuel, and high value chemicals in batch reactor, and it's easily stored under frozen conditions.
Okay, so the yeast we are going to use is called Saccharomyces cerevisiae, and also known as baker's yeast. And it is the first species which uh, dominated by the humans, and also this species cerevisiae can use glucose as a carbon source to produce ethanol and carbon dioxide. And also, as Cerevisiae is Saccharomyces is a model organism of biochemistry, genetic, and molecular biology research. Um, Using yeast as a platform have several advantages, like um, yeast has very high yield for the protein production, and it will be very stable um, during the shortage and like during the genetic engineering. And also it's cost effective because the medium is very cheap and you can reach the very high cell density during the fermentation process. And because the yeast is Saccharomyces is a kind of modeling organism, so it, the technology to engineer this species is well developed, and and also like for now there are a lot of different chemicals and protein or drug can be produced by the Saccharomyces cerevisiae. So we choose this species as our host to engineer. And so in this project, we are going to transplant a carbon fixation pathway into into Saccharomyces cerevisiae and try to um, acquire a special strain which can utilize the carbon dioxide as a carbon source to produce high volume chemicals and drugs. And and in this project, we are going to use synthetic biology tools like CRISPR and other control element to apply on this project.
Okay, here I want to introduce our project using metabolic engineering for value-added chemicals. And here we just choose shikimic acid as our target chemicals. And I've listed some basic information about shikimic acid. For the chemistry property, it's shikimic acid is a white powder at room temperature, and it's also easily to dissolve in the water. And for the biological property, it's kind of important precursor of aromatic amino acid in the organism. And as for its usage of the pharmacologically, and it can shikimic acid and its derivative can be used as anti-flu, anti-inflammatory, and anti-cancer medicine. Till now, there are three main ways to produce shikimic acid. They are extract from the Elysium verum and chemical synthesis and fermentation. So based on this, we just perform our strain engineering. So for the first one, we just want to use carbon dioxide and xylose to as can be used as a carbon source. So we just introduce the two pathway, carbon fixation pathway and xylose pathway into the yeast. There are three reasons we use that. For the first reason, because the MXR XDH module contain a mutant XR preferring NADH, XR, XDH, and XK could improve the productivity and decrease the byproduct accumulation. For the second reason, the catabolism of maltose could simultaneously supply energy and cofactors to meet the requirement for exolose metabolism. For third reason, the carbon dioxide fixation pathway may bypass the glucose repression on xylose catabolism in the cell. The carbon dioxide produced during fermentation can also form an appropriate atmosphere for ribocycle activity and redoxing for improving the cofactor balance. So after introduce two important pathways, we just want to engineer the inner pathway of the yeast to enhance the shikimic acid production. For the first one, we just engineer in the pentose phosphate pathway. We overexpress RPE and TKTA to increase the precursor of the shikimic acid, E4P. And then we just overexpress PPSA. We just want to increase the backflow of the carbon flux to also accumulate the PEP, another important precursor of shikimic pathway. And last, we just want to overexpress some key and important genes during the Shikimate pathway and also deletes the AROK and AROL to make the shikimic acid to achieve the highest titer. At last, I also want to talk about the bioreactor. There are two factors that we should be concerned. For the first one is about gravity. The gravity on Mars is only about 30% of the gravity on the Earth. So it may have an adverse effect on the fermentation process. And for the second one is if we want to make best use of carbon dioxide usage, we just want to come up with a way to do that. So in order to avoid the adverse effect or bring by gravity and make best use of carbon dioxide, we just want to minimize the reactor's volume and to achieve the best fermentation performance. Although we use the same method on the Earth, which is a feed batch culture, but I think if we just reduce the volume, we can achieve this both points at the same time. I think this is our presentation, and thanks for your listening.